Hello, and welcome to today's webinar, Using 3D Machine Vision AI and Edge Computing to Optimize Mine-to-Mill Performance, brought to you by Pit and Quarry Magazine and our sponsor of the event, Strayos. I'm Hallie from North Coast Media, the Content Marketing Manager for Pit and Quarry Magazine, and I will be your event manager for today's presentation. At this time, I'd like to get you comfortable with our council and the ways you can participate during today's presentation. Please notice the Q&A panel on the left-hand side of your console. If you have a question, type it in the panel's text box, then click Submit to place your question in queue. We encourage you to ask and enter any questions you may have for our speaker during the presentation. We will address these questions at the end of the presentation during the Q&A portion. Questions submitted during registration have already gone to our speaker and may be covered during the presentation. If you experience any technical difficulties during today's event, you may use the same Q&A panel on your screen to submit your issue, and technical support specialist Brian or I will personally assist you. Finally, you may learn more about today's speaker by viewing their bio and photo and contact information in the panel located in the upper left-hand corner of your console. Now I'd like to introduce today's speaker. Today we will be hearing from Ravi Sahu, founder and CEO of Strayos. Ravi is the founder and CEO of Strayos, a computer vision and AI software company that combines remote sensing and 3D drone data analytics to deliver mine-to-mill AI solutions. Strayos is deployed in more than 2,000 mines. Before founding Strayos, he spent more than 12 years working globally with Fortune 500 companies like AT&T, Verizon, and British Telecom in various roles, from product management to building teams for large digital transformation projects. At this time, I'll turn the presentation over to Ravi. Take it away, Ravi.
Thank you, Haley. Hello, good afternoon, everyone, or good morning. Really excited to conduct this, session and have a more kind of, dialogue about like what are the newer technologies out there that can be applied into different, scenarios of mine-to-mill applications. And we're going to be also talking about what the evolution looked like about these technologies. So please drop in your questions if you have any technology or curiosity that you have. I always love to hear about the questions. But with that said, we'll begin the topic for today, which is application of machine vision AI and edge computing, and more specific towards how do we use this to optimize our day-to-day mine-to-mill performance. A little bit more about Strayos as a company. What we do is we build AI solutions which are applied into the mining operations. We have over 30 countries our platform is used. Now we have about 3,500 mines and quarries use systems on a daily basis, over 125 customer base. And we have a global presence, a global team that allows us to do 24/7 support. Overall, a lot of the projects that has been conducted in the platform, what that means is it's been a variety of data sets, and that's where the AI model becomes a lot more powerful as it goes through the time and tested testings and these models. And we have over 190 million images have been analyzed that has led to various operational gains. And we have focused a lot more on the upstream side of the operations, such as drill and blast and the ore quality improvement here as well. I want to give a little bit more overview of like what Strayos does in a nutshell. So starting from surveying and planning, which means you can bring the data from drones, lidars, imagery, or any other scan to input, and you can apply various data processing in the platform itself, which can generate a 3D digital twin and which then utilized to do various type of analysis, such as geology analysis, drilling and blast planning, suite of optimization tools to conduct what's my planning outcome will be, and then leading into various other optimization scenarios, from that. Post-blast, various types of analysis can be conducted on the bench itself to analyze backbreak, fragmentation analysis, vibration modeling, leading to various good understanding of what's my blasting outcomes will be. And then we have various other geotechnical analysis tools as well to understand what's my compliance, high-vol compliance is, safety side, haul road analysis, as well as the rock mass characterization there. And then all this data can be also combined into one place to understand what we are tracking, which means in terms of KPI, whether we are meeting them or where are the areas for improvement. So usage of these day-to-day tools leads us to several cost benefits, as we can see, since the data is there. Now, before we now begin a lot of talks about the machine vision, I want to draw some attention about where the problem exists. And we all know in the drilling and blasting side, as well as the audience profile here probably is also a lot more on the mill and the plant side. And this what cost profile looks like. Either you are from a mining operation or a quarry operation. If you're spending $X in the drill and blast side, and if that's where a lot of the issues can be avoided, and if that's you putting a dollar value of $1 there, if that's not done right, then we have a lot more cost, almost up to 5 times in the loading and hauling side. And similarly, the cost continues to exponentially rise in the crushing side, 5 times of DNB, the screening side another 5 times, but it gets massive when we are at the stage of further processing, either at the grinding stage or further milling side, which is even more like 5 times of drill and blast. So the cost profile looks massive here. And when we think about the cost profile, everything starts with the drill and blast here, which is the start of mine to mill. And drill and blast issues stems from either drilling, design patterns, geology considerations, you name it. There are so many uncontrolled variables are there that leads to those scenarios. So not only that, drill and blast issues, stems to wasted ore and the lower production, which means you're getting low cost per ton, or just in the metal mine scenarios, a lot of dilution occurs, which only results into a lot of oversized rocks, which has adverse impact in the crusher downtime. And we always see the crusher downtime, how much money it can cost here. And we've also seen how these issues impact the energy here. And the high energy costs and the carbon emissions is one of the biggest topic and the theme that everybody is looking to address in terms of the processing circuit. And if we are producing better size at the blasting stage, we're going to obviously reduce those energy costs, and we have seen up to 10% more energy is required to crush the ore or the rock, either depends upon whatever plant you have, if it's not agreed to a required size. So we looked into the cost profile here, but everybody is looking into what's the sustainability side here, what the value we can deliver more in terms of the emissions and the sustainability. So I've gone through kind of what that looks like, for the plant here. And we think that the energy efficiency and environmental impact is a big part, where we see that we can drive massive benefits in the combination circuit. So roughly about 3% of the world's total electrical energy is consumed in the combination circuit, which is almost 50% of mine's total energy consumption. And as we have seen, an average 10% average energy is required in the crushing, which is up to 100,000 carbon emission tons. And moreover, the operating expenses and the economic viability here, energy expenditure leads into almost 10% of the mine's overall expenditure here. What that means, the more expenditure is going on my operational budget, which results into more massive reduction in the operating budgets then. Lower availability of the high-grade deposits continues to reduce now. So we have to rely on things to do it more precision, how we are mining, and then also crushing and milling as well. But there is another aspect of the sustainability here, which is your equipment downtime and the safety side. If the downtime results into massive blockages, which is equipment damages or the combination circuit, if you have a slab material that gets stuck over the screening circuit, that's a issue in itself. So your overall throughput is going down. And just in shutdown, we have seen about up to 2 to 5 days can cost into a lot of cost here if you're looking at the large mines here. When we look into the other types of objects, which is resulting into not in proper size, but also other foreign object, either a plastic or a metal piece, that is another aspect of the safety that needs to be avoided when the combination circuit is been active and running. So how 3D machine vision and edge AI can help here? So when we look into the mines or the quarries here, we almost see a lot of technology has been implemented in different stages. And we just don't realize how impactful it is until we go and dial down each use cases separately here. But this just entails how, from the technology implementation perspective and the sensor and the data, it's been capturing every day and day in and day out. But it's only in the aggregated form, which means the data is being captured, but the intelligence level is not being created on a daily basis. So when we think about the mine here, this graphic is from Nokia, which is essentially entailing the different sensors that are implemented in the mines and where the evolution is also going. So we are the drones are becoming ubiquitous now, but we're also seeing autonomous haul trucks, asset monitoring and different equipment, geo-tagging and geo-fencing of the assets. We are looking at the analytics space on how this predictive maintenance can be done for the operations equipment. So all these technologies already continue to be a major part of the mining and the quarry operations here. And once there is a lot of data, we start to see the aggregation of the data happens, but the intelligence layer always is where the bottleneck comes. So that's where I want to focus a lot more on how the edge computing can help create this intelligence layer real time. But before we dive into that, let's understand what's the evolution of these technologies are, because the machine vision comes from the imaging side of the technology bucket here. So we have to understand what that means. So we know that there are 3D imaging, what we see in terms of the display, and then there is a 3D sensing and recognition and detection side of the imaging. So when we look at the imaging, which is the stereo images, which can take photos from multiple angles and generate 3D digital twins. You have 360 images, which can be used for any inspection or just looking at the visual aspect. And the image processing, where you are looking at each pixels and rasterizing or vectorizing them to understand different measurements technique. Then you have the holographic images, which are looking at projecting an image and understanding and visualizing the different components and different aspect of your either asset or either just a digital twin there. So those are on the imaging category. Now we think about the 3D sensing, which leads to different understanding of perception, recognition, and detection side. So one of them is the mineral recognition. So another level of sensors of the imaging or camera sensors is hyperspectral or multispectral, which leads to understanding of different components and the spectral signatures of the minerals, which has heavy use on the deposit detection. Then we have also seen the applications in the equipment health detection side, so either a camera sensor or the sensing the sensors can be applied into equipments to understand not just the health, but also where are the potential damages can occur way in advance. We've looked into the sensing components into the ADAS, which is the automated driver alert systems, which are nothing but understanding the visual components of the surrounding and generating a spatial awareness, and then it sends what are the different conditions, from the driver alert needs to be built. And we also see the detection in the AR and VR side, which is the augmented reality and virtual reality. So if we can simulate the actual mine environment and or quarry environment before we actually make any decisions, what will happen? So it's a projection of the outcomes. And in this case, the blasting use cases could be understanding of what not only the bench models are, but also what type of explosives energy will have an impact. What's my drill hole conditions are there? What's my floor conditions are there before I start to load the holes? So those are great use cases for the AR and the VR from the detection and creating awareness side. And then we have also seen the obstacle avoidance, which is, again, there are sensors built in to understand and avoid things there, which leads to a third category on the sensing side, which is the situational awareness. So if I have a sensing equipment, which is the cameras supplied in several different directions, we can build situational awareness. So it means a machine can understand what's this awareness around that equipment. So 2 machines or 3 machines can talk to each other and understand about their own positions. We see these applications often in the robotics. So for today's discussion, we're going to talk more on the sensing side, which is our range of modality here. And this 3D image and sensing covers a wide array of modality. What we're going to cover in today's presentation is a lot more on the optical 3D side, which is a structure from motion, stereo cameras, and projection-based cameras, which is what the machine vision is. But there are other types of modality like X-ray scanner, CT scanner, where you see and understand the geometry and the physical aspect, data capture. And also we will see the aspect of Lidar in today's presentation. And there are different types of Lidar, which is solid state flash Lidar. What we will not cover today is more on the radar and the SAR systems here. So things to know more about the edge computing. So we looked into what machine vision components are and how it has evolved. And when we think about the edge computing, which means it allows the computing and the processing of the data real time at a local servers. That's what the edge is. So all the packaging of the software and everything, it has an ability to understand and move the data real time and understand and give an intelligence real time here. So processing power is physically close to the sensors. In this case, it's camera sensors. And that's where we see a lot of applications in the mining side, where a lot of innovative use cases can be built, because mining always deals with low latency situations, which means you don't have a high bandwidth, you don't have a good network, and you need to process the data real time. And you need a good rugged environments to process this data. And in order to build these situations where the data can be processed, the edge computing is the perfect fit there. When we think about the AI itself, where it has moved in the maturity curve here, and this is a guideline from GMG, Great Mining Group here, where they published about what are the areas when we think about the AI applications where it fits. So assistive intelligence, which means AI can execute the task that would be done by humans, which means I have A plus B related tasks are there, and what that deterministic outcomes will be. You train the model, you determine the pattern, and then the same pattern gets repeated time and time again. And decision-making is always in the user's hand, whether to recognize that the pattern that's been developed by the AI system is accurate or not. Then you have the augmented intelligence, which means it's combining the human intelligence and the AI to learn from each other, which means it's a supervised models can be developed, but it also empowers the human to generate different type of understanding what AI machines are generating. And then a combination of human intelligence can be applied to see what has been missed. So new insights can be discovered from there. Then there is another level of intelligence, which is the autonomous side. The AI system is capable of acting on insights generated by itself. And we see that a lot in the self-driving or the haul trucks, which are being autonomous now, which can understand and see and stop. We see a lot more in the robotic side. So the maturity curve at the moment in the technologies where we are a lot more at the assistive and augmented side. The autonomous is still at the stage, it is still evolving to get it the level where it can be applied on a day-to-day scenarios. So combining 3D machine vision and edge devices with AI. So we looked into what machine vision is, what the edge computing means, and then we now going to talk about how this can be combined together. And just to clarify even more further, when we think about machine vision, it's nothing but it's just the ability for a computer to see. It employs more than a variety of different cameras can be applied, and it's a simplification of analog to digital conversion. And how does that work? There are cameras which are capturing visual information in the form of videos, images, and it can process those images or videos real time on the edge devices. And this technology is often used in environment such as where you need to make real time decisions, because the processing and analysis can happen real time. And let's look at how we have evolved over the last, hundreds of, in terms of the human evolution and drawing a correlation with the machine vision and the perception side. So as a human brain, you have a touch, speech, vision, facial recognition, and coordination. And that's how our brain operates this fast. And the machine vision side, that's what we are trying to replicate, but only the vision part. The coordination, touch, and the speech doesn't happen. The vision part and the perception part happens here. And that itself is a very powerful intelligence, because now you have a lot of data to work with, from that. And in the computing power now. So when we think about kind of the perception and the understanding and the coordination, which is correlation is a machine vision there, which is the camera system. Now the computing power, the correlation is our brain. But this is where it multiplies exponentially the computing side. Over the years, or more than 300,000 years, the human brain, how it has evolved, and the smartphone chips is less than over 12 years. And if you think about the active users, we have about 7.5 billion human users and 6.5 like in the smartphone chip. But I want to draw the correlation of how the neurons, we have about 100 billion neurons, and in the smartphone chip, just in your pocket, it has 10 billion transistors. And multiply by, as the decades to come in the future, this computing power will continue to get faster and get more and more there. So doing the computation at the edge will evolve significantly as we look into the future, and we will see massive advancements in this, applications now. So where the edge systems are moving now. So the center of gravity, when we think about the edge, mining enterprises are the perfect fit. On-device intelligence is paramount. As we can see, you can process the data closest to the source, your physical sensors, and it can complement to the clouds, which means we don't have to move the data to the cloud all the time, but you can move the relevant information. And it benefits the latency issues, reliability, and privacy concerns that always emerges to move the data in the cloud goes away. And it can also support remote operations. And we can also not overload the network bandwidth that is required in moving this heavy data, which is a lot of video data, a lot of 3D imagery data here. So applying this to mind to mill, so which is the camera systems, which is the 3D stereo systems and the edge computing. And we can gather a lot of useful information that can be utilized for mine-to-mill operations and different stages here. What this system is, what we call here is the Netra system. And this is a 3D studio vision system, which has wide-angle 3D AI sensors built in. It has the ability to capture the depth information, which means how the entire physical structure measurement happens. It can capture that. And it can take 100 photos per second, which means at each frame. It can work indoor and outdoor, very resistant to different rugged mining environments here. And it also comes with a built-in IMU and the other type of sensor to stabilize and calibrate the actual hardware here. And when it combines with the edge device, which is a very high-powered GPU computing systems, so your data is processing real time, which can complement these advanced camera sensors with the computing devices here. How we can apply this into the day-to-day mill production or the plant side, either at the trucks, where the gantry, where we can install and detect the oversizes, at the loaders, at the crushers for real-time fragmentation to understand our throughput, as well as the belt to understand and continuously measure run-of-the-mill operation. So what it allows you to do is really understand and establish a benchmark for your size that's coming out from your blasting, which helps understand what's my throughput is. Either your goal is to reduce the crusher gap. This gives the data now. Understanding of the mine-to-mill energy consumption now, and which leads to a reduction in carbon emission. But more importantly, where I see the biggest benefits are, now you know the data, you can do a real-time adjustment to your plant settings now. And we have already seen use case about the foreign object detection. So how the setup works. So you have the camera systems, and then the camera is connected to the edge computing through a physical connector, which is powered by your regular power. And then the edge devices are also connected to a network. This could be various options, either just the LTE, Wi-Fi, or the hardwire. In this case, where we are transferring the data to the cloud after the results are analyzed. So AI-generated results are synchronized to the cloud. Cloud services gives you an ability to now really monitor your plant data from anywhere. So how the AI works at the edge devices, these are small devices, but very, very powerful, which means it's taking the data, as you can see the raw data. It has AI model built into this edge systems, which has multiple variable models are there. So you can see, you can do a lot of detection, segmentation, 3D analysis from this model, tracking of each particles that's been flowing through, contamination of the objects, and all those triggers can be built to understand where it is and what's the adjustment is needed. So these objects are all available in that models, which are being trained to understand and analyze and perceive this information. And this can be utilized in the dashboards to see what are the implications that we are seeing in our plant now. So this gives a little bit more understanding as you see the video being played now. What it shows, it's a depth estimation video, which means it is looking at different parts and understanding and building a true 3D understanding of different particles that's been flown here. You're not seeing the actual 3D rocks here, but you're seeing the depth, which gives you good measurements. And that's what is the power of the machine vision AI. And these GPU systems are being able to real-time process this information, even though it's a heavy data, you can see being processed in real time now. And we also look at now the actual data being flown here. So now, once I know my depth information, which means the actual physical structure, and the point cloud that's coming in will give you the high accuracy for measurements. Now, another level of insights can be developed to monitor and predict the ore content. At different stages, crushing and milling, if you have a low-grade waste that's coming, it can be eliminated from the very energy-intensive processing stream here. And you can also establish a benchmark for what size that's being blasted and what is coming to the crusher and the further stages down the primary crusher now. So how does that integrate with the plant control systems now? So once the devices are set up, as you can see, either indoor and outdoor, you have the algorithms which are continuously analyzing nonstop once it's installed. And this data can be fed to the plant control systems to understand whether we are getting the agreed size for our feed rate or not, or whether the run-of-the-mill operations for several belt in the circuits are getting the size that are supposed to be. So those can be monitored, and then this feed rate adjustment can be done, and the alerts can be set up to the plant control to adjust things based on your plant optimization program. And the operators can make the decisions as they're seeing the data. So no need to wait for a shift to end or another proactive instead of predictive, instead of what's been reactive maintenance really needed. Now you're seeing the proactive data beforehand to understand what's really needed now for my next shift as well. So planning the shift, if my blast is coming from a certain location, I can adjust the feed rate based on what I'm going to run, for today. So how it works in terms of the data capture and processing. So you set up the system in different stages of the mining circuit, either at the crusher, at the primary, or the belt operations. The data is continuously being analyzed here, and we can see the process intelligence comes out from that, which is it is scanning continuously at each passing rock, and we see that it is continuous scan, so there is no sampling of data. Every time a rock is being passed, it is using that analysis, to pass that information. And we can see the number of rocks, different aspect of flow rate as well, percent fines, and the oversize, rocks that we see. And you can also see the other aspect of the plants as well, so detection of empty belt. And this is one of the big side benefits that comes in when you know that based on my today's production, how much time where the belt was empty. So we're just running the energy while there was no production happened. Another aspect of this is screen anomalies, really understanding the size that's coming, and if it's the screens anomalies, which means the sizes are either bigger, just only a few inches, and if you're able to trap this early, we can avoid the screen damages, which is resulting into your overall equipment efficiency. You can improve your OEE time as well now. The size gradation, what it can detect is these are texture data, so it can also understand colors of the rock, and that based on that, these texture classifiers, we can also see the contamination. So whether it's a clay or if it's an actual ore that's coming, along with the anomaly side, as well as we have talked about earlier, if it's a large metal piece that's came in or a plastic, there is an alerting systems can be developed to instantly inform the operator now. So going further more detail into this, just a video demonstration here. As the crusher, primary crusher area, as you can see, the truck is instantly dumping the all rock particles. And as you can see, it is each scan each passing rock is being analyzed here. So what we build is the optical flow tracking, which means instead of just taking a look at the images and analyzing just the image, it is using the actual optical flow of that and instantly looking at each passing rock. So there is no sampling of data that allows you to give a good understanding of what is in this dump truck actual load is there. And similarly, as we see in the belt as well. So as each passing is happening of the belt, it's building a good understanding of what's my size distribution here for the belt and the run-of-the-mill operation. So allowing this information, as we see if there are oversized rocks, as you can see, those are in red. So that's not good for the operators here. So how do we build that alerting system? And this can be integrated to the feed rate now, or the just adjustments can be done, for the plant settings. So what you see in the dashboards now is the understanding of each data that's coming now is being transferred to the cloud, and you can monitor this from anywhere. Either if you have multiple plants and you're monitoring multiple operations, this allows you to have a pulse check on what happened, today. What's my shift data, or how many loads that came in, and what was the agreed size distribution for each of them. How my run-of-the-mill operation fared, for today's shift. Whether we are producing what we really needed, maybe yes, from the overall tons perspective, but what's happened? Are we producing too much fines after the primary crusher? And that's where it gives a good understanding, because the fines are made, as everybody says, in the crusher. So what we can do to avoid those crusher gaps. So this information, as you have now in the dashboard, you can start to understand really and dial down on the blasting side. So passing this information to the blasting team and working in conjunction to come up with a pattern that avoids this, scenarios of not meeting the size definition that our crusher expects. But more importantly now, as you can see, now you have a good understanding of what the data is coming and what's happening in the plant. But how do we correlate back to the mine now? And that's where this mine-to-mill tracking comes, which means geospatially tracking which blast or which shot ended in the crusher. So you have a blast pattern and the muck pile data from your mine, which means you're analyzing and designing the shot. You have the XYZ position of each drill hole data. And then after the blast happens, you have the blast fragmentation data that can be correlated now to what happened for that specific load in the crusher. And how we can do that is we apply the smart GPS tagging to each truck load that is coming to the crusher. And the camera has an identifier to correlate each timestamp along with that GPS ID for that truck or loader or whoever is, whatever type of equipment is bringing the material in at the plant. And you can specify the blast zones with the blast ID and see what's the activity as well when the material was loaded and when it was brought in at what timestamp. And all those data can be correlated to that specific load blast ID with that specific throughput of the plant as well. So another powerful correlation can be drawn now to really understand what's happening from my mine to the mill now. And what it gives you a good understanding of whether the pattern that we had performed average, best, or okay. So that's something you can start drawing. Not only that, you can also start drawing very granularly by each drill hole, which you can see how each hole energy consumption got correlated to the throughput, because now we have that location ID and the hole ID to correlate to that specific load. So the relationship between the mill throughput and powder factor can be drawn, which can be used now further to understand my correlation of what's my dry fines, wet fines, particle size that came in, and really drawing this yield improvement. So the daily yield improvement can be done for each blast now, or even further, like each day. So this data now, it's in your fingertips. It can help understand really the aspect of what's going on from start to the finish. Furthermore, now we have the data to understand. You can draw scenario analysis. So now we have the data from what's happening in the mine, what we designed the pattern, how it ended up in the crusher, or even further run of a mill. Now, if we use the same data to calibrate our next blast design, what it would look like. So the scenario analysis to understand if I change my powder factor, if I change my pattern, and am I getting the same D50, or maybe I change certain parameters now, which can result into more optimized pattern, but now I have a data to play from the mill. So having this type of analysis with the real data can really make adjustment in the pattern that you're looking for here. And predicted data, prediction that comes out is now calibrated data from the mill now. So really understanding where we want to be and how we want to go forward in each blast by blast, or maybe if your geology is changing, in order to track that as well, those map pattern considerations can be done now. So usage of all these tools allows you to build an entire optimization program from start to finish. As you can see, correlation from fragmentation with drill design, and correlation of crusher throughput data, or the crusher data, or the run-of-the-mill data further at the belt. It is hugely useful how improvements can be made at the mine, at the bench now. What it differentiates, it's all these data sometimes is very hard to handle. So you have the differentiators in terms of the AI models now, which is automatically structuring this granular data in one single place, which doesn't require any bulky integrations or workflow. You start to see this play again and again, and you can start to do the correlation. And this data can be fed from all across the value chain, and you can see this not in a siloed way, but in one single place in the database structure here to see and monitor the different conditions in a much more visual way. And it also brings contextual information, that's why geospatial contextualization is very, very important, because if you're designing a blast in the same mine in one specific pit, but then the geology changes as you're tracking down different seam, how does that impact? So geospatial understanding and layering the data in that contextual way gives you a good understanding of how each geology are performing differently now. And then correlation with the time series as well, what happened at what time series instant. So I want to draw some attention from the case studies that we have with the different types of companies that we have worked with in implementing this Netra system. So on the belt side, we have seen significant run-of-mill improvement in the operations of one of the tier 1 cement company, where they installed and to ensure their secondary feeder performs at the optimal rate. Over the 10 months, they realized significant savings and a 1.4% yield improvement from the system. Another tier 1 metal mine where they installed the crusher to track particle size at their primary crusher site. And what they realized is after integrations with their fleet management systems and the plant control system, they were able to make real-time adjustment of their crusher settings, which resulted into a huge improvement on their throughput by 7%. Another company, more on the tier 1 aggregate side, where they're able to really understand and dial down on the blasting pattern side to avoid the oversize issues that they were getting, and that was causing the crusher issues and the crusher gap. They were able to up their production by 9% by adjusting the crusher gap now. So these are all these applications by combining machine vision and edge computing can deliver. So the real benefits really comes from what the data is there and how this data is being used to build an intelligence. The systems are there. Now it's up to the plant and the mine operations after this intelligence is built to make that next corrective step where they want to take from 1.4% yield to next level now. Maybe target another 2% there. Maybe target another, crusher gap improvements or understanding of overall optimization that needs to be carried, maybe down upstream now. So with that said, I will stop here and open up for any question. Thank you very much for your attention.
Thank you, Ravi. At this time, we're going to jump into some questions we received during registration and a couple from during the presentation. Our first question is, which minerals can this be used for? Does it work in low light situations, and how accurate is it?
Yes, so from the minerals perspective, it doesn't matter, any type of minerals. It is an RGB sensor, so it's not. There is no other types of chemistry or the spectral signatures are built in. So you will see what's the gradation in terms of the size gradation, and it can be applied to any type of minerals, either metal side, coal, cement, aggregates. And I think there was a follow-up question there, Haley.
Does it work in low light situations, and how accurate is it?
Yep. So yes, it can. The lighting is definitely an important factor for the installation, where if it's a very indoor environment or a dark environment, the lighting is needed. There are various great setup for the lights. The LED lighting is very helpful. And the consistent lighting is good, which means sometimes if you're installing an outdoor environment, that's always, it's a tricky part, because when you have a sun glare, when you have sunrise, that can play a bit more, curveball here about the detection. But we have trained our model to overcome those situations, but still the lighting is definitely helpful, as we have seen in our experience. And the accuracy side, I'll be happy to share more on that, more examples. But we have seen the detection is very accurate based on the sieve size sampling that has been done, in a physical sieve size sampling, and it's been compared with that method.
Great. Where do you see AI going in mining in the next 12 months and in the next 24 months?
Yeah, another great question. We see that AI is changing a lot of things, the way we operate now in terms of the mining and the quarrying side. We see huge applications in how the blast design can be improved. So that's a very practical applications. And when we are seeing a lot more now on the plant side, predictive maintenance side, we've seen huge improvements on the autonomous, making the systems autonomous. So that's where the AI is applied. But where I see in the future, in the next 2 or 3 years, a lot more on the autonomy side, which means making the machines autonomous to really understand, making the machines perceive things. The failure breakdown, usually happens. So those are the areas where I see a lot of different applications of AI, including the workforce training and if we can generate a more knowledge-based, generative AI models are there that can be applied to really train the newer generation of workforce that's coming now, to train them very easily with the generative AI models of having a huge understanding of, let's say, a company which has almost several hundred thousands of blasts are there. And sometimes those knowledges are acquired by several years of experience. You have worked in the field for 50 years. But what if we have those blast data being applied into a generative AI model and build a knowledge base from that for someone who is coming into the workforce and really understand quickly to what last 50 years of knowledge can be distilled properly. So that's where I see a training side where the generative AI models can be utilized now.
Great, thank you. How does the camera work?
So the camera works. It's a stereoscopic system, which is a dual lens. It triangulates. It captures the images, triangulates, which builds the depth information. Depth information builds the measurements, and that's what you derive the different particle size gradation, any type of colors and texture information from that. So the sensing, optical sensing happens, and we take that data to build more applications and algorithms on top of that.
Awesome. In iron ore business, crusher is playing a vital role in producing the desired saleable material. Is there any automation process for monitoring the infeed of the crusher so that the optimum fragmentation size can be fixed?
Yeah, great point. And the question here is really towards like, how do we understand the feed size, feed rate that's coming up, and how to optimize it in real time. So now we have the data that's coming, which is really real time. So if that can be integrated with the plant control systems, you can build this, adjustment real time then. What that means is you build these recipes of if this happens, do this. And that can be done through the plant control systems. If I'm seeing a size of, if your agreed size is 40-inch, but it is the plan as the camera is detecting, and it's about 48-inch. So instantly detects, the alert can be sent in the plant controls, and these plant control systems alerts are more real time, which means as it's seen. And now if you have another trigger in the plant control to adjust this, the feed rate, which means either stop the crusher and make the secondary breaker active instantly, or just stop the crusher altogether. So all this can be built in the plant control systems to put these alerts in there.
Great. How does it handle the dusty environment?
Yes, so the dust, the camera itself, the lens is a polarized lens, which means it can remove any type of, dust, visible dust layers and everything. But if it's a very, a dust which a human eye cannot see as well, that's where we don't have an option of self-cleaning in this system. In that case, we have an alerting system where we alert the operator on the site or someone on the site. They go and they can clean the camera then.
Awesome. Are there API integrations?
Yes. The system offers the full APIs that can be integrated to any third-party applications or your database. It's a fairly simple process of just hooking up and with a webhook, and it moves the data.
Great. How small of material can you monitor on a belt application?
Yeah, so that's a pretty good, precise question here, because sometimes if you say how small it can monitor, it depends upon where it's installed. So now in the belt, what we have seen in our experience, it can monitor up to 3 to 4 millimeter very easily, and install at a height of 4 to 5 meter. But if you lower it to to a 2 millimeter, even it can go even lower in the size of the detection as well.
How do you take into account blending between different patterns?
Yeah, so the blending between different patterns here that's where I see a lot of really powerful information can be gleaned on. Which means if you are shooting 30% info and the blend, a blended product, or if you're just shooting other types of product there, and if you run through the crusher, you will see that, right? How exactly the crusher performed. So now I have something to play, and if you are able to, because now you have each shot, you may be putting one shot here, another shot here, and you have shot with a different pattern or into different explosives itself, you will see that what the load performed. So we can draw that differentiation of what that load was there to see each pattern understanding from there. So this separation can happen because it's based on the timestamp and the different equipment IDs which are bringing those material to the crusher. So those information can be very, very impactful of how you make the blasting optimization decisions.
Awesome. I'm curious, how can your vision system determine or grade as indicated in one of the presentation slides?
Yes, so well, I should clarify that it's a size grade. We don't determine chemistry at the moment. It's all based on the right now the texture, so it can determine the colors and the contamination, and then the size. The chemistry of the rock is not determined through the sensors. For that, there are other advanced sensors are there, as I mentioned, the hyperspectral side.
And we will take one more final question, which is the color coding based on wavelength absorption of the rock or fluorescence imaging?
So the colors right now is just based on training the rock data, which means we can see the texture information, and that's how we are looking at each kind of pixel information and building that kind of color information there. We are not using any type of wavelength information because again that's more on the spectral side. That's related to the chemistry side. Our detection for the colors are entirely based on the pixel information.
Okay, excellent. Thanks, Ravi, for a great presentation today. Now we will wrap up the live event. Thank you all for attending the Using 3D Machine Vision, AI, and Edge Computing to Optimize Mine-to-Mill Performance, brought to you by Pit and Quarry Magazine and our sponsor of the event, Strayos. A recording of this webinar and other upcoming webinars from Pit and Quarry will be posted to pitandquarry.com/webinars. Thank you all for attending, and we hope you will join us again soon for another great webinar.
Thank you.